Hello. 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 Okay. Hello. Oh, okay. So, good evening to one and all present here. And this is the last class, that is week 12 of online uh, problem solving session of the Transport Phenomena course, whose instructor is Professor Dasgupta of IT Kharagpur. And I am the current TA of this course. So, as this is the last class, we'll be carrying forward with only problem solving. That is like not any of the theoretical questions, just numerical question we'll go through. And these questions, as it is transport phenomena, so will be a combination of heat, mass, and fluid. So, let us proceed to the first question of today's session. Okay. So for the first question, there is a plane surface of that is a 25 centimeter width, has 25 centimeter width, and its temperature is maintained at 80 degrees Celsius. So it is a plate. So there will be heat transfer from this parallel plate. And atmospheric air at 25 degrees Celsius flows parallel to the surface with a velocity of 2 meter per second. Okay, so using the results of boundary layer analysis, we got some values like these equations are already given in the question itself. The skin friction and the overall the average skin friction formula, and the drag force formula, and the Stanton number of heat transfer formula. And the fluid properties are also given. We have to determine the following for the 1 meter long plate. So this is the interface of the question number 1, 2, 3 as it is linked question. So let us proceed to the first question. So the first question is the mean skin coefficient, mean coefficient of skin friction. So the mean skin friction coefficient we have to find out approximate value of this. So this is the first question for today, and using the previous equations, that is, let me proceed to the previous one. Yeah, in this slide everything is given. So first, by finding out the Reynolds number, you can understand, okay, which equation you will use, and what will be the total skin friction coefficient. That is the average skin friction coefficient. And the equations are already given here, so you can use them for the calculation. I'll give you 2 minutes for solving this, and then we'll proceed to the solution itself. Okay, I hope I'm audible and visible. So, for the first question, we have to first find the Reynolds number. So, Reynolds number is LV by nu. So, that is L is 1, it's given 1 meter long plate, right? And nu is, V is 2.8 and nu is 1.807 in 10 to the power minus 5, right? So this will give us 1.55 into 10 to the power 5, that is less than 5 into 10 to the power 5. This is transition Reynolds number. Okay, so critical Reynolds number. So what happens above this? There is turbulent flow, and below this there is laminar flow. So this flow is laminar. Okay, so the skin friction coefficient CFL is equal to 1.328 into Reynolds number to the power minus 0.5. So that is equal to 0.00337. Okay. So what option is this? Let us proceed to the question first. This is a question. So the option is 0.033. So that is option A. Right. Now let us proceed to question number B. Question number 2. This is question number 1. Right. Let's proceed to question number 2. Question number 2, the total drag force approximately in millinewtons exerted on the pipe by here. So we have to find out the drag force. We'll take 2 minutes for this question and then we'll proceed with the solutions. Okay, let us proceed to the second question now, where we have to find the drag force. So the drag force on the plate is given by FD is equal to CFL area rho V square by 2, right? Because CFL we know that FD upon area into rho V square by 2. So this is only represented as this 0.0037. This we already found out here, and 0.25 the area into 1. 0.25 into 1 is the area, 0.25 width, and 1 is the length. 1.087 and 2.8 square. Density into velocity square by 2. This gives us 3.59 millinewton. So what is the answer among okay, here answer is option B, right? Now let us proceed to the next question. The total rate of heat transfer approximately in what from the plate to the airstream. We have to find out now what? We have to find out the total rate of heat transfer. I'll give you again 2 minutes for this, for solving this, and then we'll proceed with the solution itself. I hope you have solved this. If not, then let us proceed. Okay, so we have to find out the heat transfer. So heat transfer, we know that EQ is equal to HA delta T, right? Now, using Colburn analogy, STL is equal to CFL by 2 Prandtl number to the power minus 2 by 3. This we already found out from here. Let us proceed to the first slide. It is already given, right? Standard number Prandtl number 2 by 3 is equal to CF by 2. There only, from that only we have found this. Right. So now that is equal to H by rho CPV. Now H is equal to 2.133 into 10 to the power minus 3, 1.087, 1008, 2.8 is equal to 6.45, 54 watt per meter square per Kelvin. Therefore, heat transfer Q is equal to HA delta T is equal to 6.54 into 0.25 into 1 into 80 minus 25. That is equal to 89.925 watt is equal to 90 watt is approximately is equal to 90. That is answer is option D. Okay. Now let us proceed to question number 4. That is also a linked question. Today we'll do 3 linked questions. That is 3 into 3 9 linked questions. Okay. Now next problem is in a spherical. This is mass transfer based problem. In a spherical pellet of 1 × 10⁻² meter is sprayed with a very thin coat of paint. The paint contains volatile solvent to dry the pellet in an airstream of 300 Kelvin and 1.1013 × 5 Pascal pressure is used with a bulk velocity of 1 meter per second. The estimated loading of the solvent in the wet paint is 0.12 gram solvent per centimeter cube. Physical properties are given. There is vapor pressure of solvent is given as 1.27 10 to the power 4 Pascal. Mass diffusivity of solvent in air is 9.63 10 to the power minus 6 meters per second. Kinematic viscosity of air is 1.569 10 to the power minus 5 meters per second. And density of air is 1.177 kg per meter cube. The thermal conductivity of air is 2.624 into 10 to the power minus 2. And thermal diffusivity of air is 2.219 and 2.216 in 10 to the power minus 5. And heat capacity of air is 1.1006 joule per gram Kelvin. Molecular weight of solvent is 78 gram per gram mole. So, using the analogy is already given. Choose the closest value of mass transfer coefficient Kc. Sorry, not first question number 4. Using this Nusselt number relation and Reynolds number relation is also given. Choose the closest value of heat transfer coefficient first. So let us solve this question. We'll take 5 minutes to solve this question and then we'll carry on with the solution itself. Okay, about this problem, let us proceed to the solution now. First is Nusselt's number is given as 0.37, Reynolds number 0.6, Prandtl number to the power 1 by 3. Reynolds number dp is equal to u infinity d by mu is equal to 1 into 0.1, 1.569 to 10 to the power minus 5 is equal to 637. Then we'll find out the Prandtl number. Prandtl number is mu upon alpha, that is equal to 1.569 into 10 to the power minus 5. That is 2 upon 2.216 into 10 to the power minus 5. That is 0.708. Now, Nusselt's number is equal to h d by k. H is equal to Nusselt's number k by d. So we'll replace Nusselt's number here in the main equation. Okay. So this becomes okay. H becomes 0.37 637 to the power 0.6 0.708 to the power 1 by 3 and 0.02624 upon 0.01. So this becomes 41.65 watt per meter square Kelvin. Okay, so this is option, as we can see from the option, this is option A, correct? Okay, let us proceed to the question number 5. Here the analogy is already given and we have to choose the closest value of the mass transfer coefficient the same way. So analogy is given the same way as we have already done in the momentum transfer equation, the previous problem we've already done. In the same way we'll do here. Sorry, in the heat transfer problem for the Nusselt's number, same way we will do here. You note down this equation. I'm opening these two slides at one time. Four to 5 and question number 5. Slide. You can use this values. And this is the equation. First note down the equation and then use the values. If you have any doubt, you can ask for the same. Okay, so first of all, we'll write the equation that is already analogy that is already given to us. Infinity Prandtl number to the power 2 by 3 Kc infinity Smith number to the power 2 by 3. Kc is equal to h upon rho Cp. Kc is equal to h upon rho Cp. Prandtl number upon Smith number to the power 2 by 3. Okay. So Smith number is equal to nu upon dAB. That we already know. Nu is given as 1.569 10 to the power minus 5 upon 9. dAB is 9.62 10 to the power minus 6. 1.63. Okay. So now Kc is equal to 41.65. H is 41.65 upon 1.177 into 1.1006. This is rho into Cp. Now Prandtl number is 0.708 upon 1.63. Smith number is 1.63 to the power 2 by 3. Prandtl number is 1.708. 1.708. 0.708. Prandtl number is 0.708 and Smith number is 1.63. So this gives us Kc to be 0.020 meter per second. This answer is, which one is this? Is B. Okay. Now let us proceed to sixth question. Question number 6. Choose the closest value of the molar flux of solvent into the air stream. So we have to find out the molar flux of the solvent into the air stream. I'm giving this page onto display. You have to find out the molar flux. We'll take 5 minutes for this and then we'll proceed with the solution. I'll wait for someone to solve this. Otherwise, we'll go on with the solutions. Okay. Just open the question first. First, NA is equal to KC. NA is equal to KC into CAS minus T infinity. CAS is equal to P naught upon RT. That is the vapor pressure of air upon RT. That is equal to 1.27 at 10 to the power 4. That is already given in the question. 8.314 into temperature is given 3. 5 point, this gives us 5.09 mole per meter cube. But C infinity is equal to 0. Therefore, NA we get as 0.020. AC is given 0.0. KC already found out now. 0.020 into 5.09. That gives us 0.102 mole per meter square. This is option C. 0. Okay. Now, question number 7. Let us proceed to the question number 7 now. Okay. The engine oil at 100 degrees Celsius and a velocity of 0.1 meter per second flows over both surfaces of a 1 meter long plate, maintained at 20 degrees Celsius. The properties of the oil are under like properties are given as density is given, nu, that is the kinematic viscosity is given, K is given, that is thermal conductivity, coefficient of thermal conductivity, and Prandtl number is also given. Determine the thermal boundary layer thickness at the trailing edge. Choose the closest value among the following. So we have to find out the thermal boundary layer thickness at the trailing edge. I'll give you 3 minutes for solving this, and then we'll proceed with the solution itself. First, you have to find out for every of this type of question, you have to find out the Reynolds number first, and whether it is laminar or turbulent. Depending upon that, you will decide what the boundary layer thickness equation will be. Like for laminar flow, one equation is there. For turbulent flow, another equation will be used. So based upon the Reynolds number, you will choose the equation. Okay. Uh, so for this question, we determine thermal boundary layer thickness. So first we'll find the Reynolds number. The Reynolds number is U infinity L by Ni. That is 0.1 into 1 into 86.1, sorry, 10 to the power minus 6. This is 1161. Hence, this gives the flow is laminar. Cause for flat plate, if it is less than 5 into 10 to the power 5, the flow is laminar. The flow is laminar, so at x is equal to L. So delta is equal to 5L by Reynolds number 5.0. Because we know this is delta by x is equal to 5.0 by root over Reynolds number. Right? This is the equation. So here we'll get 0.147 meter. Now question number 8. Determine the local heat flux for the same condition mentioned in problem 3 and the trailing edge. Determine the local heat flux for the same conditions. We have to find out the local heat flux. As simple. I am opening this question and we have to find out the local heat flux. So for local heat flux, you already know the equation. Let's proceed to problem 3. This equation only will be using. Okay, so I'm opening this equation and you just you already know for laminar flow the heat flux equation. So using that equation will be, for your simplicity, let me write out the equation itself. So Nusselt's number is equal to K by L into 0.332 Reynolds number Nusselt's number is equal to 0.332 Reynolds number 1 by 2 Prandtl number 1 by 3. Use this equation and from here you find out the local heat flux. I'll give you 2 minutes for this and then we'll proceed with the solution. Okay, by using this equation, if you'll find out the local heat transfer coefficient, that is K upon L. Nusselt's number is HL by K, right? So we can break it down to HL is equal to K upon L into 0.332, Reynolds number to the power 1 by 2, Reynolds number to the power 1 by 3, right? So if we will solve this, putting every values, we will get local heat transfer coefficient is 16.25 watt per meter square. So this is now let us proceed to the next question. Now we have to determine the total heat transfer rate per unit width of the plate. Total heat transfer rate we have to determine. I'll open up this data sheet and you can find out that the solution to that problem. Okay, for the previous problem I have not solved the whole one. Okay, we have to find out the local heat flux, right? We have just yet find out the heat transfer coefficient. So the local heat flux will be HL Ts minus T infinity, that is 16.25 into 20 minus 100 watt per meter square. That is equal to minus 1300 watt per meter square. This is option A. Okay. Now question number 9. We have to find out the total heat transfer rate per unit width of the plate. Total heat transfer rate we have to find out. I have opened the data sheet. You find out the total heat transfer rate. I'll give it 2 minutes and then we'll proceed with the solution. Okay, so for as we know, this flow is laminar. So for laminar flow, the average heat transfer coefficient over a distance 0 to L is twice the local value of H. This we already know for laminar flow. Now, for laminar flow, the average heat transfer coefficient is twice of the local heat transfer coefficient. That is equal to 2 twice of H L. So this is 32.5 watt per meter square Kelvin. So the total heat transfer rate per unit width of the plate is Q is equal to 2 into L into HL bar into Ts minus T infinite. That is, in this case, 5200 watt per meter. So that is option B. Right, option B. Okay, we are done with question number 9. Now let us proceed to the question number 10. For flow over a flat plate with extremely rough surface, the convection heat transfer effects are known to be corrected by the expression. So the surface is rough of the flat plate, and for that the Nusselt's number equation is given. For airflow at 50 meter per second, what is the surface shear stress at x is equal to 1 meter from the leading edge of the plate? Assume the air to be 300 Kelvin, and for 300 Kelvin the properties are given. So we have to choose the closest value of the surface shear stress at x is equal to 1 meter. Okay, you will take 4 minutes to solve this, and then we'll proceed with the solution. first the Nusselt's number is given as 0.04, Reynolds number to the power 0.9, Prandtl number to the power 1/3. Reynolds number is equal to LV rho by mu is equal to LV by mu is equal to 1 into 50 upon 1.589 into 10 to the power minus 5 is equal to 3.1 into 10 to the power 6, far greater than 5 into 10 to the power 5. So the law is turbulent. Right. So Nusselt's number gives 0.04 into 3.1 into 10 to the power 6, and Reynolds number to the power 0.9 into 0.7 to the power 1 is equal to 24697. From Colburn analogy, it is already given from Colburn analogy, center number to Prandtl number to the power 2/3 is equal to CF by 2. So same thing, center number into Prandtl number, we use this analogy. So Stanton number heat transfer is equal to Nusselt's number by Reynolds number into Prandtl number. Nusselt's number we found out 24697 upon 3.1 into 10 to the power 6, and Reynolds number, Prandtl number is 0.7. So this gives 0.011. Now 0.011 into 0.7 to the power 2/3 is equal to CF by 2, or CF, skin friction, is equal to 0.017. So CF is equal to shear stress, wall shear stress upon half rho u infinity square. So shear stress is equal to 24.67 kg per meter second square. So shear stress is equal to 25 kg per meter second square. 25 approximately is equal to 25 kg per meter second square. So this, if we look into the option, this is option B, right? Now let us proceed to the next question. We have 2 more questions left, 3 in fact. Okay, so the first question, for unsteady state heat conduction in an iron sphere of 1 inch diameter has following physical properties, that is already given here. Initially the sphere is at temperature 70 degree Fahrenheit. What is the thermal diffusivity of the sphere? If the sphere is suddenly plunged into large body of fluid of temperature 270 degree Fahrenheit, how much time is needed for the center of the sphere to attain the temperature of 120 degree Fahrenheit? A sphere of same size and same initial temperature but made of another material requires twice as long for the center to reach 128 degree Fahrenheit. What is the thermal diffusivity? Okay, so this is question number 10, right? This is question number 10. 11. Okay, so I'll give you 5 minutes for this, for solving this, and then we'll proceed with the solution. This is very easy problem. First, thermal diffusivity we'll find out. Thermal diffusivity formula we already know, K by rho Cp. And then the by using that transient thermal transient temperature equation, that T minus T center minus T naught for lumped parameter model. We already know that for lump parameter model equation, if you use, we'll find out the answer to the next problem. That is the B part of the question number 11. And by seeing the alpha, that is the thermal diffusivity relation with the time. By taking that ratio, we can find out the answer to the problem number, like problem number 11, C part. Okay, so the part A, the first part is the thermal diffusivity. Thermal diffusivity, we know alpha is equal to K by rho Cp. So K is already given as 30, rho is given as 436, and Cp is given as 0.12. So this reduced to 0.573 feet square per hour. So the second part is B is the center temperature is 128 degree Fahrenheit. Right. So for the transient equation, if we apply Tc minus T naught upon T1 minus T naught, there is the surface temperature, this is center temperature. So 128 minus 70 upon 270 minus 70. This gives 0.29. Now we know this is equal to alpha T by R square, that is 0.1. So T from here, that is 0.1. So T from here gives 0.1 into R square by alpha, that gives 0.1 into 1 by 24 whole square by 0.573. So here R square, that is R is equal to 1 by 2, diameter is 1 inch, so R is equal to 1 by 2 inch, so that is equal to 1 by 2 into 12 feet, so 1 by 24 feet. So time becomes 3.03 into 10 to the power minus 4 hours is equal to 1.1 seconds. Now C part is by equating alpha 1 T1 by R1, because right hand side of both is same. So alpha 1 T1 R1 by equating the dimensionless times alpha 2 T2 by R2. So alpha 2 becomes as alpha 1 T1 by T2. So this is equal to 0.573 1 by 2. Alpha 2 is equal to 0.287. Now question number 12. So the next problem is to measure the thermal diffusivity alpha is equal to K upon rho Cp of a solid material. This may not be done by measuring, this may be done by measuring the amplitude A1 and A2. So there are two sheets of solid material with a thin layer I of adhesive in between. Yes. Okay. So the total thickness is to be, so to measure the thermal diffusivity, this may be done by the amplitudes A1 and A2 at 2 points, distances Y1 and Y2 from the periodically heated surface, show that the thermal diffusivity may be estimated from the formula. And the amplitude of the temperature oscillations is the following function of Y. So the amplitude as a function of Y is given, the equation is given. First is calculate the thermal diffusivity, measure thermal diffusivity, and second is calculate the thermal diffusivity when the values of everything is given. And amplitude ratio is also given here. Okay, so I'll give you 4 minutes to solve this and then we'll proceed with the solution. I will convert them at centigrade now. Okay, so for question number 12, first we see that the amplitude of the temperature oscillations in the following are the following function, that is AY is equal to Q naught upon K root over alpha by omega exponential minus root over omega by 2 alpha y. Thus, the ratio of the amplitude for two different distances from the plane is A1 by A2 is equal to exponential minus root over omega by 2 alpha y1 minus y2. Right. Now, if we'll take logarithm on both sides, ln A1 by A2 is equal to minus root over omega by 2 alpha y1 minus y2. So this gives omega by 2 alpha y1 minus y2. This can be solved from the thermal diffusivity. This can be solved for the thermal diffusivity. That is for alpha. So we'll find alpha is equal to omega by 2 y1 minus y2 upon ln a1 by a2 whole square. So this gives 2 pi omega is equal to 2 pi nu by 2 y1 minus y2 upon ln a1 by a2 whole square. So this gives pi nu y1 minus y2 ln a1 by 8 so whole square, where nu is the frequency in cycles per second. So now in part B, nu is given as 0.0030 cycles per second. Y2 minus y1 is equal to 6.19 centimeter, and a1 by a2 is given as 6.05. So if we'll put everything here in equation of alpha, alpha is 3.14, that is pi, 3.14, 0.0030, that is nu, into 6.19 by ln y minus y1 upon ln 6.05 whole square. So this is given as, this is found as 1114 centimeter square per second. Okay, so let us proceed to the last question of today's session, and that is the last session. So the last question is force convection from a sphere in creeping flow. A sphere of diameter d whose surface is maintained at t naught is located in a fluid stream approaching with the velocity of t infinity and temperature t infinity. Okay, so the flow around the sphere is in the creeping flow regime, that is with the Reynolds number less than 0.1. Verify the equation is dimensionally correct. that is an estimate, and the second part is estimate the rate of heat transfer Q for the flow around a sphere of diameter 1 mm. The fluid is in oil at T infinity is equal to 50 degrees Celsius, moving with a velocity of 1 centimeter per second with respect to the sphere, the surface of which is at temperature 100 degrees Celsius, and the oil have the following properties as given. And the equation that is required to be used is also given here. So first we have to find out whether we have to do the dimensional analysis, and we have to see whether the equation is correct or not. And the second one is that putting the values, we have to calculate the Q, and the equation is already given here. So I'll give you 4 minutes to solve this, and then we'll proceed with the solution. Okay. So let us proceed with the last question and the solution of that, that is question number 13. Okay. So first we have to do the dimensional analysis on part A. So for Q, the dimension is mlt cube, small t cube, that is time cube. D is L, T is temperature, T, capital T, and small k is mlt cube, capital T. R is dimensionless, and Prandtl number is also dimensionless. To check dimensional consistency, ml square t cube is equal to lt mlt cube, capital T. That is, this is left hand side, we can see, is equal to right hand side. And part B. For part B, first we'll write the equation pi d square, that is already given, t naught minus t infinity k by d. Now 3 pi 2 by 3 to 7 by 3 gamma 4 by 3 dv infinity rho cp by k to the power 1 by 3 in terms of Prandtl number. So this is equal to pi d t naught minus t infinity k 3 pi to the power 2 by 3 2 to the power 7 by 3 gamma 4 by 3 into dv infinity rho cp by k 1 by 3. So we'll fill everything with the CGS units that is already given in the question. So we get Q as pi 0.1 50 30 into 10 to the power minus 4 into 4.462 by 5.04 into 0.89297, and this is 0.1 into 1.0 into 0.9 into 0.45, 3 into 10 to the power minus 4. So this is 1 by 3. So this gives Q as 0.0240 calorie per second. This is the answer. Okay, so it's already 5:13. So if anyone has any doubt, I'll give 2 minutes, 2 more minutes, that is up to 5:15. And if anyone has any doubt regarding any question or any answer or anything related to the previous class, because today is the last class, you can obviously check the videos that will be uploaded on YouTube, and you can get back to me if you have any doubt regarding the same, and I'll be happy to answer. And today also, if you'll have any doubt, you please contact me through email. Okay. I'll wait for 2 more minutes, 1 more minute up till 5:15, and then I'll end the call. Okay, so it's 5:15 already, and I'm ending today's class. I hope everything is understandable, and it was a very like thrilling course, like for explaining everyone and all of you. Uh, and this was a learning process for you and me as well. For explaining you, I have to learn as well. I have to prepare the courses and the classes and the questions itself. Okay, so if you will have any doubt again, you can mail me up. You will get all the YouTube videos, recorded YouTube videos uploaded into the YouTube channel, in my YouTube channel, and the links will be provided in your course. Like it will be, there will be a section where all the links will be provided to you. And you can visit the courses, check the courses, and if you have any doubt, you can mail me up. And regarding understanding of anything else also, you can mail. Thank you for attending the course. It was very nice. The session was very nice, and thank you. Bye bye.